you can see up here. But I'm going to start it with you on one part and then kind of set you to the point where you can kind of manage on your own. And we're going to do this part real fast, though. Okay, ready? So slide 5, okay, which occurs if an electron transitions from equals 5 equals 2. So show me, like, just visually, what does that look like when an electron goes from 5 to 2? Okay, so is it dropping? Yes. Okay, what's happening with the energy when it drops? Releasing. So we immediately narrow it down to what and what? C, or B and C, thank you. And then we need to look at visible light emitted or not emitted. Where would one find information? The Bohr model from the reference table. So we need to look at the reference table. I think it was visible light from memory, but on that specific question you guys may have said, oh, well, I should probably look at the Bohr model. But you have this Bohr model, and you look and see where that energy transition fell, and that energy transition falls. Ooh, where does it fall? 5 to 2. This is visible light, so the answer would be B. Okay. All right, and then in this one, this is a big why question. I just want to probe your mind here. Okay. So we know these isotope designations are important to giving this information about the subatomic particles. What does that 35 mean? What does 35 mean? Everybody, let's go. Atomic mass, right? So mass is composed of what plus what? Okay, so protons and neutrons, right? It doesn't tell us anything about the electrons except the fact that protons generally
are the same.
Right, generally protons, electrons are the same unless we can ion. All right, so the different atomic masses are occurring between different isotopes of the same element because what's starting to change? What subatomic particle?
Neutron.
The neutron count, right, okay. I think we could do that one. All right, gamma radiation, or when a gamma ray is emitted by an element, what happens to the atomic mass and the atomic number? Draw in the air for me what a gamma ray symbol looks like. Draw in the air for me. You guys are just drawing random letters. It's like a upside down Y thing like that. Okay, what's the mass of a gamma ray? 0. What's the proton count of a gamma ray? 0. So what should change? Nothing. So the answer should be mass stays the same, atomic number stays the same. What's an alpha particle? 4 and 2. Okay, so that's 4, 2. What's the symbol? And either an A or I heard somebody say helium. Either this or this. It's like a little fish-shaped egg. What's a beta particle? What's the top number?
0.
0. Bottom number? -1. And then symbol?
E.
Either E or 0, -1, and B, as in like a B with a long tail. It's like a Greek symbol. But regardless, we always have the top number representing mass and the bottom number representing atomic number. Okay? Okay, electron configuration. Give me it for calcium. Can you just take up on calcium? Where's that? Okay, so give me, I'm just going to point. You guys got to keep going, okay? So can you get started? 1s2, hold up. Listen up, start over. 1s2. So we went 1s2, which is hydrogen and helium collectively. We went 2s2, which is lithium and beryllium collectively. Shush. Okay, so that gets me from boron to neon, so 2p6 because we're still on the secondary level P.
3s2.
And where does that get us to?
Like sodium and
Magnesium. Gotcha. Kendall? 3p6 switches from aluminum to argon. In here?
4s2.
4s2 when we stop there. How many electrons should that represent, guys? 1s2, 2s2, 2p6.
20.
Okay, 3s2, 3p6 equals what to 18, 4p2 from 4s2 is 20. Yes.
Could we have also written it in the short notation?
Yeah, that's because there was no specifications here, but I would assume 90% of the time when you're examining using the long term, you wouldn't use shorthand, just because it would be more inclusive to include everything. Okay, we know our trends. All right, so which of these has the greatest atomic radius? look first at my yellow with your answers. And then show me how you would do that, what you're thinking in your head, or maybe you would actually literally do it on the exam. Every year I hear people go, they do this during the exam. Which hand is representing your radius?
Right.
Okay, so your right hand radius turns this way. So the radius turns, increases to which direction? Okay, so from what?
Right.
Okay, so from right to left across, from right to left on period, and then from top to bottom on group. Who's the biggest in this category, or in these answers? Cesium to the sky. Like, how many energy levels does cesium have? 1, 2, 3, 4, 5, 6. So it's got like 6 rings around it. It's very large compared to these other ones, which are smaller, and they're in the corner, and you know that their nuclear breaking charge is quite large. Okay, let's name a couple of these. Ready? I'm gonna point and chant. Go. Okay, so carbon monoxide next. Ammonium phosphate. Nitrate. Good. This one. Good. Iron 3. Iodide. Okay. There was our compounds with metallic bonds similar to ionic compounds. Ionic bonds similar to ionic compounds. So remember we made that big list of like ionics versus metallics, and that we did that like right for the solutions we didn't even begin because it's really like kind of carries through the whole year. We go on physical properties. So tell me yay or nay, okay? Both tend to have double and triple bonds. Nay, like metallic bonds don't form those kind of triple bonds, right? Both tend to have low boiling points. Nay, okay. Definitely metallic and ionic have the highest of the boiling points because we can put them on the stove and they're not going to melt, right? Or we can put salt crystals on the stove and they're not going to melt. So anything like that you experience in real life actually does apply. Both tend to have poor conductivity. Nay, because like copper wire, that's what we use in our electrical conduits to make sure we have conductivity across our household. And then D, of course, would be the right answer because it's counterbalance B. Okay? How does a single covalent bond between 2 carbon atoms compare to a double bond between 2 carbon atoms? So remember we did this. We stood up and we made bonds. Okay, can you just humor me? Make a bond person next to you. Make a single bond. Just touch them. Touch them here. All right. So this is a long, kind of weak bond because like you're just like barely touching each other, holding hands. Make a double bond. Double bond. Closer, right? So what happened with the bond length? It got shorter, so what's the right answer? Weaker and, I can't read it. Similar. Yes, ma'am. Thank you. Okay. There's only a couple more I actually want to do. Ooh, what's the empirical formula for C4H6?
C2H3.
C2H3. So you simplify the subscripts until you can't get them any simpler. Empirical formula is the simplest of all ratios. And how would you find the percent mass in aluminum? Chloride of aluminum. Okay, so what of aluminum? Okay, so grams of aluminum, which is 26.98, divided by the total mass of aluminum chloride, and then times 100 because that's a percent. And then we can convert. I know we can convert. And then, what do we generally have to use? And this of course will be provided to you on your exam. What do you have to utilize to help determine if a single replacement reaction will occur? Radioactivity series. I know ours are the blue sheets, but you get like a big single page of everything. Where I copy the HO page or 4-2 page. So the activity series, where are the most active metals or active things? The top, they're higher on the activity series. So they're definitely going to, if they're the singles, they're definitely going to go in there and try to break up some fixed bond to get in there to make the reaction occur. What do you consult for the double replacement reaction?
Solubility.
Solubility rules. And what are we looking for when we say solubility rules? The formation of a precipitate, right? That says, hey, this reaction is happening, I'm going to make a precipitate, which is one of the general observations you can make about double replacement reactions. I know you can balance, we did that recently. Remember the net ionic stuff? Right, so you write it out, you separate the charges, and then what do you call the things we cancel? Meaning they don't do anything, they watch the reaction. Spectator ions, right? So that's like what we saw in the WebQuest the web test from Friday, we saw us write the total reaction of sodium hydroxide plus hydrochloric acid yields sodium chloride and water, and then we write down the net ionic because there were some things that just weren't really doing anything. They were sitting there watching. Okay? I'm almost done. Equations, you get all your equations on your exam. Okay, effusion. So say that in your own words. What does effusion mean? Talk to me, Ruth. And talk about why or how you would determine if something effuses faster. Alright, come back to me. 3, 2, 1. Alright, so nitrogen or hydrogen, of course those mean diatomic gases because all the time whenever these gases exist by their lonesome themselves, they're in 2 or H2. Who's going to fuse faster, nitrogen or hydrogen? Why hydrogen, please? Right, it only weighs about 2 grams per mole, whereas nitrogen weighs 28 grams per mole, a lot heavier, a lot slower. So it does relate to like what you might observe in everyday life as well. What do you have to do in this question? Okay, we have to do stoic. Then you automatically see this standard temperature and pressure, and then what rings a bell? 22.4 what? Per of a gas, right? So you cannot use that value, 22.4 liters, unless you're dealing with a gas. And we definitely are here because it says ammonia, NH3 gas. What's the first step in your story? 15 grams of what? Nitrogen monoxide. Okay, and then what? Okay, so what's that, 30 grams per mole? 14 plus 16. Okay, and so we made it to nitrogen monoxide, so it's really important to write down the identity. What are we going to? Well, in the end, moles of who? Sorry, volume of who? NH3. So what's next? You guys said use what? Which is what over what? 4 moles of ammonia over 6 moles of nitrogen monoxide. So far, so good. And then what's this last step? 22.4. Okay, so 1 mole of ammonia, 22.4 liters. So we're looking at 15 over 30 is what? 1/2. What's 1/2 times 4 over 6? So what was 1/2 times 4? 2 divided by 6. 2 divided by 6 is, yeah, like a third. So a third of 22 is like 7-ish. 7.47 B. Right? So we'll come out. Okay. All right. Heat curve, or cool curve in this case, right? Because we're going down. And of course, you guys see this big word right here, raw leaves. Like, these are questions from the past 5-ish years. So if you feel good about this, you're getting a general preview of what to expect. Note there'll be some more challenging ones that we haven't discussed yet, and then there'll be some really easy ones like nomenclature questions that you should be phenomenal with. All right, so looking at this graph, data collected, uniformly cooled from 155. Why does the temperature of the sample remain constant between point X and Y? So here's X and Y. You guys tell me what's happening here. Okay, definitely horizontal means phase change. What phase change is this specifically? Okay, so gas to liquid, which means what? Condensation. So like this is of course phrased as transitioning from gas to solid and gas to liquid, maybe. Okay, solid to gas, no. Liquid to solid, no. So definitely answer is B, but they could phrase that like with the terminology of condensation or evaporation or melting and so forth, not just the state of matter provided. So note how that could be changed up a little bit. What's that? Phase diagram. And of course they've labeled ice, water, and water vapor, but we should know it's always solid, liquid, gas in terms of like the layout, general layout. Okay, so like I said, you should know this area here is what? Solid, this area here, in this area. Okay, so what occurs if the pressure, turn with me, okay? What occurs if the pressure of a substance at point F remains constant and the temperature increases to point G? So I'm crossing the barrier between what state and what state? Solid gas. Okay, solid and gas, and we know that's what phase change. Sublimation. So what's another word to call it out as sublimation? We can say the substance is what? We just rephrase sublimation. Subliming, right? So someone asked me, do I have to know what subliming means? Like, yeah, because you know what sublimation is, and it's very much the same relatively same word. And so they don't say sublimation, but they can, and they have in the past. So which example, or which answer is this? C. Okay. What equation is that? Dilution equation. So if you're going from stock samples to dilute samples, we use the dilution equation. All right, immediately synthesize ionic compounds placed in water to make an aqueous solution. Okay, so we have an aqueous ionic solution, which best describes a new ionic solution. What do you guys say? Good. We should know there. What's another word for an ion that conducts or is able to conduct electricity?
Electrolyte.
Electrolyte. So many times they'll say this solution contains electrolytes versus can conduct electricity. But no, that's very, if you know the definition, you can apply it in many ways. Definitely not going to dissolve nonpolar because ionics are extremely what? They're like extremely polar. We don't always say they're polar because a lot of times we conserve that word for just using it to describe covalent compounds. But they're like the epitome of polar because they have a positive and negative. No, solutions can conduct electricity. What are the ionic species cannot conduct electricity? What state of ionics? Solid state. Solid state, they're locked in place. So I don't have my little ionic structure in here anymore. But they're locked in place and they cannot move their ions, so they cannot conduct electricity. So aqueous, they totally can. Okay, why is potassium chloride able to dissolve in water? Who drew pictures on this one? Or at least thought of images. Okay, I'm telling you, it's going to be super helpful. Everybody knows it's extra time on this exam. You should have time to retake this thing 3 times. Okay, and if you draw pictures and then you make that you have time to go back and look and you're like, oh, I made a mistake. I drew water as, not going to tell anybody out. Is that water? No, right? That's O2H. So it's H2O, so make sure 2 H's and an O in your structure. And so that's going to help you at least realize the important components like this. So potassium is going to attract to what part of water? Okay, so potassium is positive in charge, is 1, and oxygen is going to be partially negative, so it's going to attract. So the best answer here is what? Potassium ions are attracted partial negative of oxygen. None of the other ones make sense because they're either incorrectly stating charges or they're saying positives and positives attract, and that's not the case. Okay, I think this was the last 60, you go to 64. Okay, cool. And you did this one, yeah. So we have a sample. How does the amount of heat change as 250 grams of water is heated from 5 to 30? Okay, so if we're going from 5 to 30, are there any phase changes occurring for water in that state?
No.
Okay, so we're not like hitting in those key points. Where are the key temperature points for water? 0 and 100. So there's no phase changes. So thank the Lord we are not drawing a heat curve here, right? But what is happening, if there is a delta T, right? Okay, so that delta T means that there's obviously, as temperature's changing, what else is changing? Kinetic energy. That information could be included like as a multiple choice option, but in this case we're just looking at like process of heat being absorbed as the temperature is changing. So as the temperature, so what's the right answer? D. As the temperature increases, the amount of heat energy increases. What equation comes to mind with that? Yeah, Cable's MCAT. That's technically what they could actually ask you to calculate that. This is more the conceptual understanding. As temperature rises, heat is being absorbed. Okay, so I wanted to show you that because this is going to be relevant to some of the things that are on your end of year review. So I'll go ahead and show you this now since you guys have it pulled up. You guys find the end of year review. It's under the website. Go to exam review documents, which is on the docs page, and all the way at the very, very bottom you have to hit more because there's a lot more to look at there. And at the bottom of the more, it says Honors Chemistry End of Year Review Study Guide 2014 student. So I'm telling you this now because I want you to pepper through a little bit of every day, but you are responsible for eventually the whole shebang. We'll get there. But I'm strategically giving you a little bit at a time, so one, it's more manageable, and 2, I can always say, you know what, you guys are doing awesome with this concept, swipe it, we don't need to do this from the review. So of course, feel free to get ahead, but don't get so far ahead that you're frustrated with me if I say, hey, we're not going to do a part of this, okay? So, but what I do, since this stuff's so old, it's like January, February old, you were responsible for the yellow, which you can see the yellow highlights. Yellow, 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 green, 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 green. And the green will take you a little longer because you have to draw some shapes, which might be a little bit of a throwback. You need to get some help on that. But that's due on Tuesday the 29th. Okay? And so after that, I'll start saying, okay, let's do half of the blue. Let's do all of the pink. Let's do the last section of yellow, which is the very end. And then red. We'll kind of knock those out at the end of next week. Because we're getting close to the end. Okay? All right, so I want you to take just a minute there. See where you can move on. If you want to ask somebody about, a question on the yellow, I'm not going to give you much time here. I just want you to at least see so you can ask some questions now, okay? Take 5 right now. At least design a paper to be utilized for this purpose. Take 1. Oh, and somebody asked me, do I need to print this? I need 17 pages if you want to print it, that's on you. But you can also strategically print just the tables, so you don't have to draw the tables. There might be 1 page, 2 pages that you maybe would want to print, because they're lengthy, so you don't want to print that, or you don't want to draw the whole table. And when you're doing this, label the section yellow and green so that we can be on the same page when I'm looking over your items. Oh, and I didn't tell you this. All right, so we're doing the first part together. 10 bullet points on how to speed up a chemical reaction. This is under documents. Somebody at your table can tell you what's going on, okay? All right, you guys ready? Camilla, you ready? Thank you. Take your phones out. All right, here we go. It's cheesy, but, you guys know me at this point. Okay, tell me what you're writing down. 10 bullet points. That's it. On how to speed up chemical reactions.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk to her class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half.
All right, so I know he's talking pretty fast. I'm trying to delineate a little bit up here. So he talked about collisions requiring correct orientation and collisions requiring correct energy, and that's just because that's what's required for them to literally react. They don't meet those two criteria, they don't react. You could obviously split that into 2 points. He said decreasing size, but then what did he relate that to? Like in a true experiment. Right, decreasing the volume of reaction vector. So making stuff smaller. So if I compacted you guys in a 2x2 room versus a 20x20 room, what's probably going to happen? What are you guys going to do with each other in a 2x2 room versus a 20x20? You're not going to fight. You're going to what? You're going to interact. You're going to collide more often. It's all about the word collision. So if you increase the collisions, you are going to increase the rate of reaction. So decreasing the volume should increase the number of collisions, which should increase the rate of reaction. What was the last one you just said? Increasing population, he equated that to what? Increasing number of particles, so thinking like 2 molar concentrations versus 12 molar concentrations. Which is more particles? 2 molar or 12 molar? 12 molar. So again, what are more particles going to do? Collide more. That's going to increase the collisions. And in the end, that's going to do what to the reaction rate? Say again? Speed it up.
N equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth.
All right, so he's talking about energy, right? What kind of energy do you think he's referencing? What's hydrogen? Okay, because he related it to what? To what? Some loud and proud people. Temperature, thank you. No. These are any kinds of, no, no lights, sorry. Sorry about that, guys. Okay, so increasing temperature, we should relate temperature to kinetic energy, and that fact is going to then say, okay, moving faster, kinetic energy is high. That means that they're going to meet each other more often, so collisions would, in the end, increase.
Students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? And a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
All right, so you have a general understanding on 5 ways to speed up a chemical reaction. So just noting, like, oh, I could do this, that's one thing. But then to be able to explain why that occurs is another thing. So you're going to investigate a little bit on this simulator. Okay, so we've done part A together, so check part A. You guys are going to go ahead and move on to part B. And this is going to give you baby steps. Okay, so you're going to learn a little bit more about the collision theory. And then you're going to learn a little bit more about activation energy, which we actually talked about before, but it's going to elaborate. What you absolutely have got to get through today is D, because this is the weird, you gotta use Flash, which is on Firefox, and you guys generally don't have access to that at home. So, like the Flash player itself. So, through D, if at all possible, I'm gonna see where you guys are in about 25 minutes. Go, okay? If you need earphones, because there are a couple of these things that talk, that's fine. They don't have subtitles because they're like interactives, they're not videos. Okay? But goals, life goals, you're getting through G. Okay? G is the kind of the culmination because it reminds you of all of the factors with details, and you have to write that part down. Okay? So go, do what you gotta do. Let's see where we are in about 25.